Hello, Aya.
So, happy Pi Day, everyone. So I will give you a very short talks and just talks about why we should celebrate Pi Day since we are DKU, and something a little bit about my research, which I think everybody can understand it. Okay. First, let me tell you why as DKU we should celebrate Pi Day. Okay. I believe everybody knows that in DKU, our math, well, we don't have a math department, but we have a math center, which names after Zhu Chongzhi, right? We have Zhu Chongzhi Math Center. And it's named after Zhu Chongzhi, and meanwhile, outside our campus, there is a road so-called Zhu Chongzhi Road. Does anybody who know why we call it Zhu Chongzhi Road, why we call it Zhu Chongzhi Math Center?
Zhu Chongzhi was from Kunshan.
Well, not really. Zhu Chongzhi is ancient Chinese mathematician who were born from 429 to 500. And he actually originally from Laishui and Baoding, which is a city in Hebei. What I mean, he's a Hebei person. He's not really a Jiangsu person, you know. However, we name after it simply because Zhu Chongzhi will spend a lot of time on Kunshan as a mayor. Okay, I think when it is in Liu Song dynasty or Southern Qi dynasty, he was a mayor of Kunshan, which is why we have a lot of places named after him, and he's kind of a Kunshan person. He's kind of from Kunshan, but not really, originally not from Kunshan. Well, and for Zhu Chongzhi, his main achievement, or the most famous achievement for Zhu Chongzhi, is about computing pi. Now, I believe everybody knows that pi is a very important math constant, and it can tell us a lot of things, and it can help us do a lot of things when you try to desire something, when you try to, for instance, make a well, or try to do some architecture stuff, this kind of thing. And so, to try to get a better number, better value of pi will help you to make, for instance, make well a little bit better to run, and so on, this kind of thing. And at that time, about 1,500 years ago, Zhu Chongzhi, he can already compute pi in almost 7 digits. Well, his main achievement about pi is he can compute pi is between 3.1415926 and 3.1415927. Okay, so it's almost 7 digits of pi. So this is very hard. Maybe you don't really know how hard it is, but you can try to do some computation by yourself using some method you've learned in calculus class. See how many digits you can get using the modern tool. Okay, and how could he get this kind of value of pi at this moment is unknown. Maybe you think that, okay, to get this kind of very explicit digit of pi is kind of useless. And in practice, we don't really need this kind of digit because, well, in practice, maybe we only use pi equals to 3.414, which is why we celebrate Pi Day. However, another major achievement for Zhu Chongzhi is he got some approximation ratio of pi. This is something really when you're trying to do something like engineer. He gave us two by the ratio, and one is pi is approximately 22/7. This is so-called in Chinese, it's called 约率, and in English, it's so-called the approximate ratio. And then this guy, if you try to compute it, it's about 3.14 something. And when you try to do some computation without computer, this is a very important simplification for your computation, right? Because you have a ratio instead of a lot of digits of a number. And you also find that, well, this one is not first found by Zhu Chongzhi. It was first found by, well, by very famous ancient Greek mathematician, the Archimedes. I believe everybody knows him. And well, Archimedes found it about almost several hundreds years ago, before Zhu Chongzhi. However, Zhu Chongzhi also find another ratio, which pi is approximately 355/113. Okay, and this is about 3.14159292. Then you can see that it's very accurate. The digit agree with pi with 1, 2, 3, 4, 5, 7, 1, 2, 3, 4, 5, 6. Okay, 6 digit accurate. And this is again something he did a really good job, because for this one, I think only until very recently, about 16th century, there is Dutch guy called Adrien and Tonnison. Is a Dutch mathematician. He find this similar things. It's after like almost 1,000 years. So he find it 1,000 years ahead. Okay, for this ratio. This is so-called the so-called in Chinese it's 幂律, and or in English it's so-called the close ratio. Okay, and well, after all, you can see that those kind of ratio is important, and it seems very useful when you try to do this engineering computation, numerical computation, because you don't really need to deal with a number like this. You only need to deal with a ratio. But well, the method how he get is still missing at this moment currently. However, somebody guessed that, well, Zhu Chongzhi may find it by something like this, which is a property that you can use to find well, some ratio. Okay, he used the property like this of a ratio is A/B and C/D. If it is some upper bound and lower bound, then we know that if you use A plus C divided by B plus D, then you get something in between. Okay, and then someone guessed that Zhu Chongzhi find this property about ratio, about fractions, and then what he trying to do is he tried to find this close ratio by doing like this. You have pi is between 3 and 22/7. Well, which is easier than to find the close ratio. Okay, and then what he trying to do is, okay, now this one is A over B and this one is C over D. So then if we do this addition, then we may get something better to approximate pi. Okay. However, if you just assume this is A over B, then it might not be very good approximation. So you can try to imagine this is like 3x over x. It's less than pi, it's less than 22y over 7y. Then that means we can get a good approximation saying that 3x plus 22y over x plus 7y is approximately pi. Now the problem becomes, how can we choose x and y? Well, since you have x and y are both on the top and the bottom, so we can assume that x equals to 1 and makes it a little bit easier, or divide x both sides and assume y over x is a new variable, so that you will get this is approximately pi. Okay, and he also find that pi is about 3.1415926. Then you multiply both sides by 1 plus 7y. What you will get is, okay, now is 22 minus 7 times 3.1415926 times y is about, well, 3.1415926 minus, okay? So you can get y is about, well, 15.99 and actually 9. So this is y. Maybe we should choose y to be 16. And if you choose y equals to 16 and then plug into this formula, what you get is pi is approximately 355 over 113. Okay. And this is, well, later, people guess that Zhu Tongzhi may get this ratio in this way. Accidentally or coincidentally, people find that eventually, or at this moment, currently, people would like to do some kind of approximation in a way of continual fraction. Which is something like, if you want to compute the number, the value of a number, or trying to approximate the value of a number, you can try to write it in some way. Like we know that pi has the integer part 3, right? So it must be 3 plus something less than 1. So which means you can use pi minus 3, and it is a number less than 1. And you take the reciprocal, then what you can do is you can try to find the reciprocal as some numbers which is greater than 1. And you'll find that if you use pi minus 3, then the reciprocal has the integer part 7. Okay, and then you do the same thing. You find that the reciprocal of that part of that number has the integer part 15. Okay, and so on. Maybe 1 over 1 plus, 1 over 292, and so on. And this way, to try to express a number is so-called the continuum fraction. The way of continuous fraction to write a number. And then the magic thing is, if you try to ignore the later part of your fractions, of your continuum fractions, what you will get is, if you ignore this part, you'll get pi is approximately by 3. Or if you ignore this part, you'll get pi is approximately by, or approximate ratio, okay? Other than that, if you take one additional digit or one additional ratio, what you will get is pi is approximately 333 over 106. Then, if you do it again, what you will get is 355 over 113. This is a close ratio. And it can be proved that if you try to use a ratio to approximate a number, then, well, this kind of ratio are in some sense, are the best approximation. Which is why, and the next number in this procedure is 103,993 over 33102. Which means, in some sense, this is really a good approximation, proved in modern theory. Okay? So this is everything I would like to talk about pi, about 族分制. Now, let's change to another topic for entertainment. Okay. Okay. Now let's discuss something other than this. That's just as an opening, well, opening speaking about the Pi Day, because it's Pi Day, so we have to celebrate it. Well, and especially we are in DKU, we are in Kunshan. Okay. And now let me talk something else. Let me talk about something for fun. It's about my research. Okay. This is something I'm doing, the research I'm doing. I try to make it easy for you to understand. I hope everybody can understand this kind of thing. It basically talks about, my research is basically talks about the bacteria, okay? So the bacteria is something I believe, some of you may have taken the biology class. And in biology class, you may learn that, the bacteria, they can try to move by themselves, right? So you can try to imagine this bacteria just like the human beings, and they may have some interactions and so on, okay? However, if you try to take a deep study about the bacteria, what you will find is basically for that bacteria in a petri dish, what they will do is they will do two things, okay? First thing is, since they are bacteria, they are not as smart as us. So what they will do is they will try to do some random work, move randomly, okay? And meanwhile, they are some small piece of creatures, right? So other than doing random work, they also need to do something as creature, as something not so stupid. This is so-called chemotaxis, which means the bacteria will try to release some chemical stuff. Or something I don't know, but some chemical stuff. And the bacteria, if some other bacteria can feel, okay, there are a lot of this kind of bacteria, this kind of chemical stuff, then they will try to move towards this chemical stuff. This is so-called, they can attract each other by some chemical stuff. This is chemotaxis, okay? This is a way how the bacteria will survive. They will try to keep everybody gathering together. Maybe at this moment, we shouldn't gather, we shouldn't do any gathering, but for bacteria, they would like to get together. That will make them stronger, okay? So these two are basic motion, the basic principle of the motion of bacteria. Then what we're trying to do is, we will try to do some study based on these two behaviors of bacteria. Now what you can imagine is, suppose you have some bacteria in a petri dish. If you do not have a lot of bacteria, then basically they try to attract with each other. However, they will meanwhile do some random work, right? They are very stupid. They just do some random work. So, then that means even though they try to gather together, but it is almost impossible for them to get together, right? Because they don't listen to any rules. They try to get around all over the world. This is a bad behavior, but they will do it like that. So if you do not have a lot of bacteria, however, if you have a lot of bacteria, then maybe at some center of the bacteria, for instance, at the very beginning, you already have some point such that it already have a lot of bacteria, then it is very attractive. It is very attractive for bacteria. It's like a big city. It's like Beijing or Shanghai. So of course, everybody would like to go to that city. And even though they try to do some random work, but it's still very, very attractive. So eventually, everybody would like to get together. So this is what the bacteria will do. Okay. And then what we would like to do. We are human beings, we couldn't think in the view of bacteria, right? So what we're trying to think about is, sometimes, for instance, we would like to kill them, right? They would like to survive, but we don't really want them to survive. So in some sense, we would like to try to separate them, to ask them to distribute evenly on your petri dish, so that if we want to kill them, we just need to, make the density of some chemical stuff a little bit higher, then it will kill them, right? So this is what we want to do. Then the problem is how we could do it like that. How we can make this bacteria distribute evenly. Well, this is just like you have a cup of, you want to make a cup of coffee, right? And then at the very beginning, you put some coffee powder in it, and then everybody adjust in one dot, right? And if you want to make it a good coffee, what you're trying to do is you're trying to stir it. So we can imagine, is that what we need to do? Or is that what we can do to make this bacteria spread evenly? Yeah, stirring a cup of soup, right? And we believe that definitely works, right? Because this after all are just bacteria. So if we work strong, if we are quite stronger, if we work hard enough, then of course the bacteria will not be able to gather together, right? We're not able to accumulate at one point for this kind of thing. That should work, right? However, if you try to think this kind of procedure, then you will find that it may not always work. For instance, if I'm the bacteria, for instance, I'm somewhere here. I'm somewhere here. And then I find that the center has a lot of bacteria, so it's very attractive for me. Okay, then probably we should go to the center. I should go to the center if no other force. So I will go directly to the center. Okay. And now, suppose you stir this cup as something like stirring a cup of coffee, like radius metric, this kind of stirring. The problem is, if I'm the bacteria, I'm still able to get to the center, right? I can just walk like a sparrow. And eventually, I still get into the center. I'm not really stupid. I can still get there. Better late than never, right? So we can still get there. So that means, okay, if you just simply stir it, just like stirring a cup of water or a cup of coffee, it may not work as good as we thought. Then the problem is, then how can we really stir something like stirring a cup of water or stirring the milk on the water to make it distribute evenly, to mix the water and the bacteria? How can we do it like that? Well, here comes to the math. In math, the hardest part and the most important part is not those kind of theory, it's not those kind of lemmas, is the definition. The hardest part for this problem would be, how should you define we can mix something? Okay, what is mixing? This is something you should ask you if you try to model a problem. Okay, so let me give you an example. For instance, we have this part, this well, black part or the green part is well, it's oil, okay, and this white part is a water. Then the problem is you try to mix the oil and water. Then maybe eventually you get these three kind of pictures. And my question is, if you get these three kind of pictures, which one you think has better mixing for the water and oil? Well,
like
yes, everybody
third one?
is right. The third
Third
one
one.
is something better, right? It should be better mixing than the figure 2. It should be better mixing than the figure 1. Okay. So in this kind of intuition, what we should get about this kind of intuition is, well, how could we define some quantity such that the third one is bigger or smaller than the second one, is bigger or smaller than the first one, right? How can we model them by some numbers or by some mathematical concept? And
Okay, like random radiuses, like random points with some small radiuses, and if the density inside is like small enough, then we pass the test.
Very good point. That's a very good point. Yes, this is a very good point. You try to check, like using a microscopy, to check whether somewhere here you get well. If you use a microscopy to see somewhere here, then you only see water, right? But if you get the same scales of microscope to see somewhere here, then you get both water and oil, right? So which means this would be a very good way to define well, how mixed you get. To use some well, particular scale of microscope, and then to see, okay, which one you can use a smaller scale to look.
So basically, so how well or hello. I want to ask. So basically, how well a mixture is mixed depends on the accuracy of our measurement.
Well, that's yes, that's what I mean, right? So basically, the measurement we trying to say, this is actually two things. The mixer is something you try to get something in a better situation, right? And how can you define a situation is better than this situation is better than this one? Then you need the definition, okay? And how can you define that? You can define by saying that, okay, if you use a microscope under the scale like this one, then you cannot see, okay, here you got a big dot of a big part of water and no oil at all. But if you use the same scale on this part, then probably you get both water and oil. So this is basically the one idea about how you can define, okay, how you can say this one has a better mix, is better mix than this one, okay? So we didn't talk about the mixer at this moment. We just say that, how can you say this is better than this one? But that kind of definition is good. However, it's still a little bit too complicated. You can try to define it in some other way, which makes it a little bit easier. For instance, well, suppose you have the density function of the water and oil. Oil equals to 1, water equals to 0. Okay, this function here on this part, it equals to 1. On this part, it equals to 0. Then what you can also imagine is, okay, it jumps from 1 to 0 on the first picture. It jumps from 1 to 0, 1 to 0, 1 to 0, 0 to 1, 0 to 1, 1 to 0, 0, 1 to 0, 0 to 1, 0 to 1 on the second picture. And on the third picture, it changes, well, the fluctuation becomes even bigger, right? So we can make it even easier to say that if we try to measure something in the sense of, well, changing, to measure a function in the sense of changing, then probably we want to take the derivative, right? If we try to take the derivative of this density function, and then we take a summation of all the changes, it could be seen as a quantity to measure how mixed you get. Okay, so you can see that you can also define this way. You check how big change you have at each point and take a summation. You take the derivative and take the integral. Okay, this is from the calculus. In practice, we don't really use this one because this one has something, it has something not so good. So we use so-called the dual space of this kind of thing. Okay, but basically, you can imagine we measure something mixed well or not by saying that whether it oscillates a lot or not. Okay? Okay, and now we have this kind of definition about which one has a better mixing. Then the next problem is, you mentioned that the next thing we need to discuss is, how we can make, the water and oil to this kind of situation. How we can choose a better mixer. This is something not so easy. For the water oil picture, what you can do is you can do it like a checkerboard. Okay, you can play as a checkerboard. And then this kind of way can somehow mix this water oil into this checkerboard thing. Okay, you play with it, you try to push and push back, this kind of thing. Then what you can get is something with a better mixer, with a better mixing property. This water and oil mix better. Okay. This is good. And however, in the sense of bacteria, does it work for our bacteria stuff? Can we use this kind of mixing skill on the bacteria, on the petri dish of bacteria, so that it can make it distribute evenly? First, we have to make this kind of situations in general. The generalization is made by, these two peoples by a paper. And, the generalization says that if you do not have this very regular water and oil, if you have some part becomes bacteria, some part is just water, then you can still make this kind of mixing stuff. Okay, assume your bacteria will not move. Then you can still do this kind of thing. This is what our human being can do. And then, later we also find that although it doesn't really work well for stirring a cup of coffee, you try to stirring a cup of coffee like this, and it doesn't work well, as we said. However, if you try to stir your cup of coffee like this, which is you have a cup of coffee, then you try to cut your cup into a lot of small pieces, and then you try to stir on each pieces. If you do it like that, then basically you can still make a perfect cup of coffee. Okay? So if you try to do it like this, then basically if you try to use this method for the bacteria, what you can do is something like this. You can see that those bacteria, if at the very beginning, they try to do some random work. Meanwhile, at the center, this is a two-dimensional picture, so try to imagine it's a two-dimensional picture. At the center, you get some bacteria. There are a lot of bacteria, so it's very attractive for others. So everybody would like to get into this center. Okay, and then the random work will try to separate them because to the center is just one direction. However, the random work will give you evenly distributed direction for the bacteria to work, right? So which means you can think random work is trying to drag is trying to push your bacteria to not go to the center. Okay, so if you only have the bacteria distribute like this around one disk, then okay, everybody would like to go to the center if you have a lot. However, if we try to mix the bacteria, what happens is the bacteria will somehow become separate. Then if you bacteria become somehow separately, then what happens is the distribution of the bacteria will become somehow steeper. Okay, you have somehow very high density at one point, but very steep, and then becomes almost no density, almost no bacteria very soon. So in this kind of situation, the random walk will become pretty strong. Okay, because it's very steep. It's very easy for random walk to push this up to separate those kind of bacteria bigger than the chemotaxis, so that it's easier for us to make the bacteria distribute evenly on your Petri dish. Okay. If we only do mixing, then as we mentioned before, this kind of way doesn't really work, but it works simply because your random walk will help you. Okay, your random walk will help you to drag this kind of bacteria to not to get to the center. Okay, so basically what we have proved is, well, for any kind of distribution of bacteria, we are able to mix them if they only do the random walk and this kind of chemotaxis. Okay, we are able to mix them. Sounds very trivial, however, this is mathematically not so trivial. Okay, and there is a very good example for you guys to, for instance, do an application of this kind of bacteria. That is the coral reefs. This is this is a coral reefs, and our model for bacteria can somehow, although it's not really, but somehow we can use it to the bacteria for the reproducing of the for the reproducing of the coral reefs, because you can imagine the coral reefs is just something on the water. This coral reefs will release some kind of eggs and sperm, and then if the water can somehow mix the eggs and sperms, then it's easier for the coral reefs to reproduce. Okay, so this is some kind of application other than this bacteria for our theory. Okay, so that's basically all I want to share with you, and thank you for attending. Let me know if you have any question. Okay, feel free to ask.
So I have a question, Professor. You introduced that divide into 4 blocks and then stirring. So is that like the only way to like optimize the mixing, or are there any other better ones?
It's not the only way. Definitely not the only way. You see, I mentioned that there are a series of work by a lot of people who design different kind of ways to try to do a mixing of some stuff. However, most of the ways are really theoretical in some sense. So you cannot really use it in practice. But the so-called the cellular flow can work in practice. Right? It's much easier in practice to use.
All right. And another question is that you mentioned that random flow tends to pull the bacteria away from the chemotaxis. That still seems kind of counterintuitive, because it is random walk. So
yes, it is random walk. Try to think it this way, okay? You have a Petri dish, okay? And the chemotaxis is what? The chemotaxis is for every bacteria. You should go to the center, right? So in every bacteria, it will have one direction that the axis asks you to go, okay? How about the random walk? The random walk is, it has all the directions, has the same probability to ask your bacteria to move, right? So which means, compare with this one direction, all the other directions will have a force to drag your bacteria, which can be seen as something to fight with this chemotaxis. The random fight with the chemotaxis.
And if you have different areas of stirring, you sort of create different blocks of chemotaxis. So basically, you mix bacteria better because they're concentrated in different places.
Exactly. So this is why we try to make it. We try to mix all kind of this chemotaxis to distribute evenly. Okay, this point we're trying to make this kind of city, kind of smaller city. Okay.
Oh, I see. Okay.
Beijing and Shanghai, we want just some smaller city.
Yeah, and like so you said that divided into 4 blocks, like the one you presented, is the only one that seems more applicable. So what are some applications? Are there like blenders designed to mix
unfortunately
like that?
Unfortunately, not really. Well, it's still in theory, it's closer to practice. However, it's still far away from practice. That's a very well. Any other question?
Thank you.
Welcome. Any other question?
Oh, when you were talking about mixing of coffee, I kind of recalled, like, you know, this fixed point theorem by Brouwer, when he talks about, like, you know, stirring is usually a continuous process of like, you know, changes of particles. So yeah, like no matter what way you would try to stir your coffee, like there would be at least one point that stayed in the same place that it was. And I was just thinking it's kind of interesting, because if it would just randomly happen that your most attractive point stayed on the same place, it doesn't really
That's a
help.
very good point. That's a very good point. So which is why this is called a Poincaré theory, something like a Poincaré theory in dynamical system. This is a very good point, which is why sometimes if you do not design your mixing flow or your mixer in a very careful way, then it may not work. Okay, for instance, if the coffee powder just keeps in somewhere that is a fixed point of your flow, of your stirring, right? Then it will never move. It will always be a big portion of your coffee powder, right? So, which is why you must be somehow very carefully, depends on your initial situation to design your mixer. Okay. So, which is why, well, in general, you should expect your mixing skill to be time dependent instead of time independent. However, if you use a cellular flow to cut your coffee cup into a lot of small pieces and then try to mix each one, if you try to use this kind of method, then what you can expect is, well, if you cut your coffee cup in some very small scale, then it's enough. Okay, it can mix up to that scale in some sense.
Well, I kind of didn't actually. Yeah, I recall there was a question I had. So, but like usually, practically, your cellars wouldn't be that small, and so if it would happen,
that's why we cannot use it in practice. Exactly.
Okay. Well.
Yeah. So this is only a math theory, which is why this is not really something practical. Yeah. This is just about math. It's nothing about something else. For instance, this is relevant to this coral reefs. This is relevant to bacteria. However, these biologists are not really interested in our result because it's far away from the real life, unfortunately.
But there is still an importance to this kind of results, right?
Yes, because we oversimplify the models because, well, if you make the model slightly harder, then it's much harder for us to study in mathematical way.
So there should be like a theoretical importance for this kind of examples. Like, what is the potential importance of this?
Well, theoretically, it just shows the existence. It just shows that our intuition is correct, okay? Because you can see that mixing can always make this kind of bacteria distribute evenly, right? This is from our intuition. It has to work. However, mathematically, we have to prove it. This is why theoretically it is important. We have
But
to
also,
prove something seems obvious for us, but not really.
but also, can you like use it just, I don't know, like because sometimes like modeling something drive a theoretical like progress further. Can this be just,
Well,
or like
some of
maybe
them,
because it has like
yes. For some of them, yes.
maybe?
But well, at this moment, our theory cannot make this cannot give any inspiration to the biologist at this moment. No. Maybe if you are interested, you can try to make some biological explanation for the theory, and that will really good. That will be a really good research project. Any other question?
I'm sorry, what theory did she ask about? I didn't catch it.
What theory? What?
I was asking about some kind of theory. I didn't hear it clearly. What was it called?
The fixed point theorem by Brouwer.
Yeah, Brouwer fixed point theory, or I think the
was broken. What are you saying?
Theory should be the Poincaré theory in dynamical system, which is also in your OD books, but I don't think it will. You will go through that theorem this semester because it's more complicated. Anyway, I think I should stop here, and I already take more time than I thought, so I'll also stop recording.